Hello there and welcome back to the Science Sleepy Minds. Tonight you're cradling a warm mug of coffee. The room is dim, quiet, just the soft hum of the refrigerator in the background, and maybe the occasional rustle of your blanket. You bring the cup to your lips, breathing in the rich scent when your elbow, somehow always in the wrong place, knocks it just so. Coffee sloshes over the edge, splashes the table, dribbles onto your leg. You flinch, a sigh, and you watch, slightly mesmerised, as the dark liquid settles into the fibres of your jeans. What you don't do is sit there waiting for it to jump back in. That's entropy in motion, and tonight you're going to fall asleep slowly unravelling why nothing, literally nothing, ever puts itself back together again. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And I'd love to know, where in the world are you tuning in from tonight and what time is it? Drop it in the comments below. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You're still watching the coffee spread out, darkening into a slow puddle that seems almost content in its mess. If this were a cartoon, maybe the liquid would shiver, gather itself like a jellyfish, and slurp right back into the cup. But it doesn't. And not because you're unlucky or clumsy. Because this is the rule, not the exception. Entropy is that rule. It's why every dropped mug shatters, but no amount of staring will unshatter it. Why a sandcastle erodes into chaos, but no beach has ever spat out a perfect turret by accident. You don't live in a universe of backward miracles. You live in one where things fall apart. Physicists call it the arrow of time, this one-way street you're constantly travelling down. No turning back, no pause button, and no rewinds. Entropy is the invisible driver. The further along you go, the messier things get. Now here's something to tuck behind your ear. The laws of physics, in their cold, mathematical precision, actually don't care about time going forward or backward. The equations that govern the movement of atoms, light and gravity, they work just as well in reverse. But your coffee? It's not coming back. That's where entropy steps in, like a cosmic referee yelling, "Play fair," every time you try to cheat reality by imagining things reversing. One chilly morning in 1865, the Austrian physicist Rudolf Clausius gave entropy its name. He'd been poking around in the world of steam engines, trying to figure out why no machine could ever be 100% efficient. The math kept spitting back a similar idea. Energy spreads out. It disperses. The more you use it, the less useful it becomes. Like your motivation after lunch, entropy is measured disorder, and nature loves disorder. A tidy room? That's low entropy. There's only one way for all your socks to be folded and aligned by colour and softness. But a messy room? Oh, the possibilities are endless. Socks in the freezer? Why not? Hairbrush in the salad bowl? Classic. There are just so many more ways for things to be messy than neat. So guess what happens when no one's watching? Chaos wins, every time. Still, not everyone's convinced we know exactly why. Historians of science and physicists still argue whether entropy is a true physical property or more of a statistical trend, a way of saying, this is just how things usually go. Maybe, they say, it's not a law so much as a likelihood, a nudge, not a push. But for you, in this dim moment of post-coffee spill reflection, entropy feels pretty real. It also explains why time only flows in one direction. You can move forward into more disorder, but back into order? That would require all the molecules in your pants, your cup, and the air to coordinate their dance perfectly, like a billion billiard balls unbreaking and rolling themselves back into a perfect rack. It's not impossible in theory, it's just so wildly improbable that you'd have to wait longer than the age of the universe to see it happen. Fun thought, if you had a time machine, would entropy let you use it? Would your body even function backward in time? Would digestion reverse? Would your brain unthink thoughts? The laws of physics say maybe. But entropy whispers, nope, not likely. And then there's the curious case of Sir Arthur Eddington, who coined the phrase time's arrow back in 1927. He said, and I quote, "If your theory is found to be against the second law of thermodynamics, I can give you no hope." Charming man, definitely the type to kill the vibe at a party, but he had a point. The second law, entropy always increases, is kind of unbreakable, more than gravity, more than electromagnetism. It's why we age, why stars burn out, why every hot bath becomes lukewarm and disappointing. Now for the fringe moment of the evening, there's a theory that maybe, just maybe, entropy is an illusion. That we're part of a fluctuating pocket of low entropy in an otherwise disordered universe, like a bubble of organisation in a sea of soup. And the wild part? This little pocket might just be a blip, a momentary accident that happened to produce consciousness before it dissolves back into chaos. Sleep well with that thought. But seriously, that spilled coffee on your jeans? That's the universe doing what it does best. You reacting to it. Grabbing a towel, sighing, maybe muttering a soft curse, is your attempt to reverse the tide. And even then, it's only partial. A stain remains, heat is lost. The moment, once whole, is now fractured. Still, you can't help but admire how consistent it all is. Predictable, comforting even, that no matter how weird the day gets, some things, like entropy, never let you down. You're still holding the empty cup, still watching the last drop on the rim shimmer under your lamp. You know it's not coming back, but now you know why, and you're ready to go deeper. You're sitting there, still slightly sticky from the earlier coffee incident, wondering how something so basic, so inevitable, can feel like such a betrayal. It wasn't just a clumsy spill, it was a tiny cosmic act, ruled by one of the most uncompromising laws we know, the second law of thermodynamics. You probably never asked to learn thermodynamics before bed, but here we are. Don't worry, you don't need to do any math. You just need to understand one sentence. Entropy always increases. That's it. That's the second law in a sleepy little nutshell. The universe does not like order. It tolerates it briefly, like a party guest who stays 5 minutes too long and then politely escorts it out the back door while tossing confetti made of chaos. Now let's unpack that a little. You've probably heard of the first law of thermodynamics. It's the classic energy cannot be created or destroyed bit. Energy just changes forms, like electricity becoming heat in your laptop, or emotional energy turning into rage when your laptop freezes mid-email. But the second law is sneakier. It tells you that while energy can change forms, it won't always be useful afterward. It gets degraded, spread out, less concentrated, less able to do work. Imagine a child after a sugar crash. Technically still full of energy, but definitely not productive. That's entropy in action. Here's a cozy example. You're boiling pasta. The burner heats the pot, which heats the water, which cooks your sad late-night spaghetti. The water gets hot, and some heat escapes into the kitchen air. That escaped heat, you're never getting it back. It's still energy, yes, but now it's aimless. It's thermal background noise, like the cosmic equivalent of losing your AirPods in the couch cushions. This is what Clausius was wrestling with back in the 19th century. He was deep in the age of steam, trains huffing across Europe, factories rumbling into existence, and the big question was, why can't we make a perfect machine? Why does every engine, no matter how polished or clever, always waste some energy? Because entropy. Once energy is spread out evenly, it's like jam on too many slices of toast. You can't scrape it back into the jar. There's no cosmic refund policy. And here's the twist. Entropy doesn't just suggest this will happen, it guarantees it. Unless, of course, you're Maxwell's demon, but we'll get to that sneaky little imp later. Back to your spaghetti. You finish cooking, turn off the burner and notice something quiet and true. Everything is cooling down. The water, the pot, the air, it's all evening out. No part of your kitchen is getting hotter unless you add new energy to it. The natural flow is always toward balance, toward disorder. You never see the room spontaneously heating the pot. That would be a reverse flow of entropy, and that's not allowed, not here, not anywhere. The universe isn't being cruel, it's just being efficient and irreversible. Historians still argue whether entropy is something real, something that exists as a physical substance, or whether it's just a mathematical description of how systems behave statistically. Like flipping coins and seeing more messy outcomes than neat ones. Is it a force, or just a way of counting possibilities? You drift closer to sleep just imagining two physicists in tweed jackets arguing softly over tea about this at Oxford, probably next to a roaring fire and a pile of forgotten equations. Now, before you go thinking this whole entropy thing is just about heat and wasted kitchen energy, let's step back and go big, really big. Entropy isn't just a rule in your stovetop universe, it scales up, way up. The entire universe is slowly slipping from a concentrated state of energy into one of diffusion, of maximum entropy. One day, trillions upon trillions of years from now, there won't be any stars left to shine. No temperature differences to harness, just a cold, even flat spread of particles and radiation, the cosmic heat death. But don't worry, you've got time, at least enough to finish your spaghetti. Now for something a bit stranger. You might think, okay, if entropy always increases, what about life? What about growth and complexity and new things being created all the time? Good question. That's the loophole. Life, as it turns out, creates local order by increasing entropy elsewhere. You, cozy in bed, are a temporary self-organizing system that consumes energy, maybe from pasta, and radiates heat and waste. You're like a little walking entropy engine, generating more disorder around you while keeping a brief, precious pocket of order inside your cells. The second law isn't being broken, it's just being obeyed in style. Now here's your quirky fact for the night. The term entropy comes from the Greek en, meaning in, and tropos, meaning transformation. So literally it's the inward transformation, a poetic name for what is essentially a slow, universal unravelling. And yet, despite its precision, people have been misquoting it ever since. It doesn't mean everything becomes chaos instantly. It means that given time, everything moves from the unlikely to the likely, from order to disorder, from hot and cold to lukewarm sameness. There's a famous thought experiment where someone imagines a shuffled deck of cards slowly returning to a perfect new deck, ace to king, suit by suit. It could happen, the math allows it, but it's so statistically unlikely it's practically impossible, like trying to untoast toast, or reverse your childhood. You could wait billions of years and never see it. The second law of thermodynamics is, in that sense, not just a law, it's a kind of destiny, a slow decline into equilibrium, whispered by every melting popsicle, every rotting banana, every dying star. And yet, it doesn't feel bad. Not really. Because within that inevitable drift, there's still warmth, there's still coffee, even if it's spilled, there's still you, a little pocket of organised atoms resisting the tide for a while longer. As you lie back, maybe adjusting your pillow just slightly, you feel it. That subtle pull toward stillness, toward balance, toward the even, soft hum of things winding down. And you realise the universe isn't in a hurry, it's just following the rules, one irreversible moment at a time. You're lying there now, quiet and warm under the covers, still thinking about that spilled coffee, the second law, and the inevitable creep of disorder. But a rebellious little voice in your mind whispers, wait, what if I could beat entropy? Enter Maxwell's demon. No, not a literal demon, though the name does sound like it belongs in a gothic horror novel, right next to a candelabra and a haunted harpsichord. This demon is more like a thought experiment with attitude, a tiny hypothetical being dreamt up in 1867 by James Clerk Maxwell, same Maxwell who gave us equations that basically explain how light works, so, bit of a brain on him. Imagine this, you have a box of gas. The molecules are all bouncing around randomly, like toddlers at a birthday party after someone handed out pixie sticks. Now, put a partition in the middle of the box. On that partition, add a tiny door and station a minuscule clever creature, Maxwell's demon, right there at the doorway. The demon's job? To let only fast-moving particles through to the right side of the box and only slow ones to the left. Over time, the right side gets hotter and the left side gets colder. Suddenly you have a temperature difference, and guess what? You've reduced entropy. You've created order out of chaos without using any energy. Or so it seems. It's a trick, a cheat code, a loophole so tempting it almost feels like cosmic treason. But here's the twist. The demon can't really do this for free. Modern physicists later pointed out that in order to measure, record and sort those gas particles, the demon itself must consume energy and generate entropy, just like you do when trying to organise your sock drawer. And unless you've hired a team of unpaid gnomes, the act of sorting things costs something. Even thinking costs energy. So in the end, entropy wins again. The universe doesn't allow free miracles. Even your imaginary friends need a snack break. But the story doesn't end there. Maxwell's demon has stayed in the scientific imagination for over 150 years. It pops up in debates about quantum information theory, computational physics, and even thermodynamics and biology. Some researchers still argue whether some form of demon-like efficiency might exist at the quantum level, where particles seem to know things they shouldn't, and decisions can be probabilistic rather than deterministic. It's that familiar phrase again. Historians and physicists still argue whether Maxwell's demon truly violates the second law, or if it just dances very cleverly along the edge of what's allowed. You shift your weight slightly under the covers, picturing this smug little imp in a lab coat sipping espresso while opening microscopic doors in a gas chamber. It's almost endearing, really, but don't get too attached to the demon. It's just one of many attempts humans have made to outwit entropy. Another was Loschmidt's paradox. This one's less demonic, but just as mind-bending. Joseph Loschmidt pointed out in the 1870s that if the laws of physics are time-symmetric, that is, they work the same forwards and backwards, then why can't entropy decrease if we just reverse the velocities of all the particles? In theory, if you reversed every single particle's movement perfectly, your coffee would unspill, your egg would unbreak, and your socks would leap back into the drawer, folded. But you can't do that. You can't even reverse one molecule, let alone all of them. It's like trying to unblend a smoothie by blowing into it with a straw. So even though the laws technically allow reversibility, entropy is what tells you. Sure, you could go back, but you won't. It's not about possibility, it's about probability. The chances of every particle just so happening to return to an earlier ordered state is so astronomically low, it's essentially zero. You'd have better luck trying to unscramble an omelette by whispering sweet nothings into the pan. Still, the idea that entropy is all about probability changes the game a bit. It tells you that while disorder is inevitable in the long run, short-term pockets of order can, and do, happen. Like snowflakes, like crystals, like you. Your very existence is a temporary localized defiance of entropy. Not because you're breaking the rules, but because you're a part of the grander balancing act. While you create order inside, thinking, dreaming, maintaining your body, you generate disorder outside. Heat, waste, motion. The price of being structured is spreading a little chaos into the world, and honestly, that feels kind of fair. Now here's a wonderfully strange fact to sprinkle on top of all this. In 2010, researchers created a real-world device that behaved like a Maxwell's demon, at the nanoscale. Using information about particle positions, they could extract energy from seemingly random motion. It was tiny, delicate, and nowhere near perpetual motion. But it made people stop and blink. Maybe, they wondered, information itself is a kind of fuel. It's a growing field, information thermodynamics, a realm where the boundary between knowing and doing starts to blur. That's right. In the modern view, information has entropy. Every time you erase a file, flip a bit, or delete a message from your ex, you're increasing entropy somewhere. It's called Landauer's principle, and it says that erasing information costs energy. So your hard drive isn't just storing photos, it's juggling thermodynamic consequences. Suddenly all those browser tabs you never close, they're practically a heat engine. You stretch a little, smiling at the thought. Even the digital world can't escape entropy. The more we organize, the more disorder we create somewhere else. Entropy is the ultimate tax. Even if Maxwell's demon had a tiny clipboard, a degree in particle sorting, and all the free time in the world, he still couldn't dodge the bill. So the lesson? You can flirt with entropy. You can dance around it, play tricks, and delay the inevitable. But in the end, the universe will collect what it's owed. Which sounds grim, until you realize that without entropy nothing would ever happen. No heat, no reactions, no change. No time, no coffee to spill in the first place. That's the paradox. Entropy is both the villain and the engine of existence. And that little demon, still sitting there, holding open the world's tiniest door, probably wishing he'd just gone into accounting. The fridge hums softly in the background, a mechanical lullaby you've probably tuned out, until now. You shift your attention to it, not just as an appliance, but as a battleground. Because behind that plastic door, nestled among the leftovers and the week-old grapes, you're witnessing a daily fight against entropy. Let's open the fridge, gently of course. No sudden movements, we're still in sleepy science mode. There's that carrot, probably limp, maybe not yet a science experiment, but close. It used to be crisp, bright, full of potential. Now it's fading, slowly succumbing to time and thermodynamics. Entropy has found its way in, even here. But here's the thing, the fridge tries. It fights back with every watt of energy it can draw from the wall. It's a cold box designed to resist the natural flow of heat. And why does heat want in? Because of entropy. Left alone, things don't stay cold. The heat from your kitchen wants to seep in to balance the temperatures. The fridge, bless its little compressor heart, is pushing that heat back out again, using electricity to maintain a temperature difference that nature desperately wants to erase. You're not just refrigerating your snacks, you're paying an ongoing toll to keep entropy at bay. This is thermodynamics in practice. Entropy always increases unless you add energy to the system. That's why your ice cream stays solid until someone unplugs the fridge. Once the power goes out, the cold escapes, the heat seeps in, and entropy rejoices with a slow, sticky melt. Here's a neat historical nugget. The first mechanical refrigerator was invented in 1834 by Jacob Perkins. Before that, people relied on ice harvested from lakes and stored in giant ice houses, literal warehouses of frozen water. A beautiful concept, stockpiling low entropy for a hot day. Back then, they understood the stakes even without the jargon. Keep the cold in, keep the decay out, keep the milk from becoming a living entity. But even with our modern refrigeration tech, you can't stop entropy. You can only relocate it. The back of your fridge, the coils, the compressor, are hot for a reason. That heat isn't just a byproduct, it's the cost of order. Your fridge is a tiny factory that exports entropy to keep its interior temporarily tidy. And you're the one paying the electric bill. Let's pause on that carrot again. It's not just aging, it's chemically unwinding. The complex structures that made it a vegetable, cell walls, sugars, water content, are breaking down. Molecules are shifting into more probable configurations, more disordered states. That's entropy doing its slow dance through biology. Which brings us to food safety. Here's a quirky fringe fact. In Japan, there's a restaurant that dry ages sushi. Yep, raw fish, aged like steak. It's a delicate balance of flavour, bacteria, and yes, entropy management. Because even gourmet dishes are just delaying decay. Of course, the battle against entropy doesn't end at your fridge door. It's the same principle in your AC unit, your freezer, your body's internal temperature regulation. Every one of those systems is in an exhausting sprint against thermodynamic collapse. You might not feel it, but you are quite literally burning calories to stay warm. And when you're cold, you're burning more. Your body is a remarkably efficient furnace designed to fight the natural spread of heat, keeping some parts hotter than others, maintaining a fragile equilibrium that entropy would love to mess up. But you knew this already, didn't you? Not in words, but in feeling. That little shiver when the room cools, the sigh of relief when the fridge light clicks on. You know that cold things don't stay cold. That heat doesn't stay put. That freshness fades, no matter how tightly you wrap it. And here's where it gets fun. You might think entropy always means mess, but it's more subtle than that. It's not about visual chaos, dirty dishes, tangled cables, laundry mountains. It's about statistical probability. There are more ways for molecules to be randomly spread out than to be neatly arranged. That's all. Entropy just says, more likely, and lets the odds do the rest. That carrot? It has a near infinite number of ways to fall apart and only one really specific way to be fresh and crunchy. So as time goes on, the odds shift. The structure collapses, the juice leaks, the crispness fades. It's not malicious, it's just math. And even the fridge, so noble, so cold, is playing a losing game. Unless you intervene, unless you crank the dial colder, burn more electricity, sacrifice more order elsewhere. Because you can keep things fresh, temporarily, but you'll pay the price. Every oasis of order you create demands energy from somewhere else. And that's the great trade-off of thermodynamics. Localized order requires global disorder. Here's another historical twist. In the early 20th century, physicists began seeing entropy not just as a thermal thing, but as an informational one. The link between information and entropy would eventually become a cornerstone of modern computing. Why? Because information, how we store it, erase it, hide it, follows the same rules. That fridge magnet with the shopping list? That's not just paper, it's stored data, a low entropy object. But leave it too close to a heat vent and the ink blurs, the paper curls, and the message dissolves. Entropy wins again. Even your memory fades. Your to-do list, your grocery items, your deep commitment to buying kale this time, it all gets fuzzier over time, unless refreshed, rehearsed, rewritten. A fridge magnet is just a memory outside your head. So you close the fridge now. The carrot sighs. The battle continues in silence. And as you turn away, the hum behind you carries a deeper meaning. It's not just a sound, it's resistance. It's your fridge whispering, not today, entropy. Not on my watch. But even it knows, one day, the plug will be pulled, the cold will seep out, and the carrot will finally be free to go soft in peace. Until then, though, enjoy the chill. Appreciate the momentary order, the stillness of the shelves, the structure of your lunch plans. Because entropy may be patient, but so are we. You step outside for a moment. The night air brushes your face with a gentle coolness, the sky spread wide above you, quiet, starlit, eternal, or at least that's how it seems. But even now, even out here in the calm dark, entropy is moving, slowly, relentlessly, all across the cosmos. It's not just your fridge, the entire universe is winding down. Let's talk about the ultimate fate of everything, the heat death of the universe. Sounds dramatic, right? Like something an edgy sci-fi villain might rant about, but it's not fiction, it's physics. And unlike most end-of-the-world stories, this one isn't loud or explosive. It's silent, slow, freezing. Here's how it works. Right now, the universe is dynamic. Stars burn, galaxies spin, planets orbit. You heat your tea in the microwave and occasionally forget it there. All of that is possible because energy is unevenly distributed. Some places are hot, others are cold. That difference, that gradient, is what makes things happen. Heat flows, water falls, light radiates. That's life, that's motion. But entropy doesn't like gradients. It wants balance, uniformity, the same bland temperature everywhere. So over trillions of years, stars will exhaust their nuclear fuel. They'll die, some with a bang, some with a quiet puff, and leave behind white dwarfs, neutron stars, black holes. Even those will eventually cool, dim, and disappear. All the usable energy will spread out. No more hotspots, no more contrast, just one giant cosmic meh. At that point, entropy hits its maximum. No more work can be done, no more change, no more time really. Not as we experience it. Just a cold, flat nothing. The heat death. But don't worry, it's not coming anytime soon. We're talking timescales so long they make the age of the pyramid seem like a sneeze. Here's a comforting historical fact. The idea of a dying universe isn't new. Even in the 1800s, scientists like Lord Kelvin speculated that energy, once spread too thin, would leave the universe lifeless. The term heat death was born from these early thermodynamic musings, proof that even Victorian gentlemen in waistcoats like to think about the end of all things over tea. Of course, not everyone agrees entirely. Some cosmologists argue whether the heat death is the final chapter, or if the universe has another trick up its sleeve, like a big bounce, a new cycle, or some surprise cosmic event that resets the game. That phrase again, historians and scientists still argue whether the heat death is inevitable, or just one possibility on a very long menu. But based on current understanding, here's the sleepy summary. We're drifting toward uniformity, a time when temperature is the same everywhere, and nothing exciting ever happens again. Sounds bleak? Maybe. But also, strangely peaceful. Imagine it. A universe so quiet that it can't even remember what noise was. No explosions, no storms, no deadlines. Just a vast, still field of barely moving particles floating through an endless cold. A cosmic nap, if you will. But in the meantime, we've got a lot of story left to tell. Back here in the present, you might be wondering, if the universe is heading toward entropy's victory, why does anything complex or beautiful exist at all? Why stars? Why galaxies? Why you? Because we're in the middle of the story. Right after the Big Bang, the universe was hot and uniform, but filled with potential. Tiny quantum fluctuations in that early soup led to clumps. Clumps led to gravity. Gravity pulled matter together. Matter formed stars, planets, cities, chocolate. Entropy increased, but in doing so, it allowed complexity to emerge. That's the trick. Entropy increases, but not evenly. Local pockets of order, like stars, like life, can form as long as the total disorder goes up. It's like making a sandcastle on a beach. The castle is structured, neat and cute, but you had to mess up a bunch of smooth sand to make it. Entropy rises overall, even though you built something beautiful. So the stars themselves, the bright specks above you, are not violations of the second law. They're consequences of it. A star is a heat engine, a blazing reactor turning hydrogen into helium, spitting light and warmth into the cold. But it only shines because there's somewhere colder for the heat to go. The difference between hot and cold drives the glow. And slowly, as it radiates energy into space, the star becomes less capable of doing work. It's burning through its ability to be remarkable, and one day, it will fade. Even the black holes, the trash compactors of the universe, aren't immune. For decades, people thought they were the ultimate entropy monsters, swallowing light, mass, information, everything. But then Stephen Hawking came along in the 1970s with a fringe but now mainstream idea. Black holes evaporate. Over vast timescales, they leak radiation, Hawking radiation, and eventually vanish. Even the universe's most voracious beasts can't escape thermodynamic justice. And in their final moments, entropy wins. Again. Let's take a step back from the cosmic for a second and return to you, this soft, breathing pocket of order tucked in a blanket. You exist in the Goldilocks zone of entropy, enough structure to form stars and chemistry, but enough chaos to allow movement and time. If the universe were too ordered, nothing would happen. Too chaotic and everything would dissolve instantly, but here we are, balanced on the edge. Even now, as you sink deeper into rest, your body cools fractionally. Your thoughts slow. You shift closer to equilibrium, not in a bad way, just in the way of things. And entropy, it's still moving, still spreading, but not in anger, not in malice, just doing what it does. So the next time you look up at the stars, remember, they're not timeless, they're mid-sentence. Brilliant burning reminders that even beauty obeys the second law, and someday in the far-off future, when the last star flickers out and the last black hole sighs its final breath, the universe will settle into stillness. Not dead, just done. And maybe, just maybe, that's the final piece. You're back inside now, cozy and a little more humbled than before. You've seen how even stars, those ancient furnaces, will eventually fizzle out. But here you are, alive and complex and wonderfully temporary. It almost feels like you're cheating, doesn't it? Being ordered in a universe that keeps trying to undo itself. Welcome to the quiet rebellion called life. You lie there, breathing steadily, and maybe for the first time tonight you start to feel the weirdness of being alive. Not just conscious, but structured. Your cells are tiny factories, your organs cooperating systems, your mind a whispering cloud of organized information. All this order right here wrapped in a blanket, and yet, the universe clearly favors disorder. So how does life get away with it? The answer is both simple and brilliant. You don't break the second law of thermodynamics, you play within it. Life doesn't defy entropy, it uses it. Like an expert surfer riding a collapsing wave, life stays upright by moving with the chaos, not against it. Here's the secret. Entropy can increase overall, even if small patches of order emerge for a little while. Take a tree, for instance. It grows from a seed into a majestic tower of wood and leaves, highly structured, complex, almost defiant. But to do that, it sucks in sunlight, energy, water, carbon dioxide, and minerals. It takes raw chaos from the world and organizes it. And in the process, it releases heat, oxygen, and metabolic waste. The entropy of the system as a whole, the tree plus its environment, still increases. That's the loophole. You, yes, you, are a tiny pocket of organized matter temporarily fighting the tide. But you're not exempt. Every breath you take, every slice of pizza you digest, contributes to the grand ledger of entropy. You're like a little entropy machine, taking in low entropy materials like food and oxygen, converting them into higher entropy outputs, heat and waste, and using the leftover energy to hold your cells together a little longer. And that's not bleak, that's magnificent, because in the face of a universe that's sliding toward homogeneity, life insists on a symmetry, pattern, intention, for a while. Historically speaking, this idea rattled some cages. In the 19th century, when scientists first began grappling with thermodynamics and Darwin's theory of evolution, there was real tension. How could life, so structured and purposeful, emerge in a universe governed by decay? But the two aren't in conflict. In fact, they're dance partners. Entropy sets the stage. Evolution dances on it. Life needs entropy. You can't have metabolism, reproduction, or movement without a flow of energy, and you can't have energy flow without an energy gradient. That means a difference in temperature or concentration, a hot thing next to a cold thing, a high-pressure region next to a low-pressure one. Once those differences disappear, once entropy has evened them out, life stops dancing. That's why your body needs to stay within a very specific temperature range. That's why ecosystems rely on the sun, a constant blazing source of low entropy energy. The Earth is like a little entropy processing plant. The sun sends high quality energy in, sunlight. Earth radiates low quality energy out, infrared heat. And life flourishes in the middle, skimming a little structure from the stream. But don't get too romantic. Life is still a renter, not an owner, and eventually the lease is up. Still, while it lasts. Life is remarkably good at delaying the inevitable. Cells copy themselves, organisms repair damage, some even go dormant, hibernating, freezing or forming spores, pausing their entropy contributions for a time. Here's a quirky tidbit. There's a creature called the tardigrade, also known as the water bear. You've probably seen its chubby, wrinkled, microscopic form floating around science memes. These little guys can survive boiling, freezing, radiation, even space vacuum. How? By entering a state called cryptobiosis, basically pressing pause on entropy for a while. But even tardigrades don't cheat death forever. They're just really, really good at stalling. And then there's you, a soft-bodied, warm-blooded, slightly over-caffeinated creature who has to manage entropy every waking hour. You eat to replace structure, you sleep to restore internal order, you heal, you sweat. You even think in ways that counteract cognitive entropy, organizing memories, making sense of chaos. But all this has a cost. Remember earlier how we talked about refrigerators exporting entropy to stay cold? You do the same. Your body radiates heat into the environment. Your waste products, carbon dioxide, urea, old skin cells, are the receipts of your ongoing exchange with the universe. This is why complex life didn't emerge until there were steady sources of usable energy. On Earth, that meant the sun. In deep-sea vents, it meant geothermal heat. Wherever life forms, there must be a gradient, a way to push the entropy somewhere else. And if you want a slightly unhinged image to sleep on, consider this. Some scientists have described life as entropy farming. That is, living systems exist because they accelerate the process of energy dispersion. They increase entropy faster than if they weren't there. Yep, you're not just resisting the tide, you're helping it flow. So the next time you hear someone say life is unnatural or against nature, feel free to mumble through your pillow. Actually, life is entropy's favourite intern. Now let's bring this back to scale. When you zoom out far enough, everything alive right now is just a flicker in a universe that's gradually smoothing itself out. But zoom in, and you see detail. You see wonder. You see a planet full of self-replicating chemical systems, all humming along, pushing against the grain for a little more time. You see birds building nests, beavers damming rivers, humans stacking dishes only for them to fall over, all temporary victories over disorder, all little rebellions. Even consciousness, this strange silent monologue in your head, is a pattern, a structure built on top of electrical and chemical gradients. You think, therefore you defy entropy, but only briefly. Because here's the unspoken rule of life. All systems tend toward disorder, but while they last, they get to dance in the sunlight. And that's enough. The egg hits the pan with a soft splutch, the yolk gleaming, the whites spreading like melting glass. You watch the transformation, liquid to solid, translucent to opaque, as the heat seeps in from the burner below. It's oddly satisfying, alchemical almost. But once it cooks, you know, there's no going back. That egg is never going to unfry itself, and why not? Because of entropy, of course. You're getting the hang of this now. But what if we told you that breaking eggs and building stars are governed by the exact same principle? That's not poetic license, it's physics. The frying of an egg and the forging of a star are both processes of energy redistribution, of matter shifting into more probable disordered states, just on slightly different scales. One happens in a skillet, the other across light years of space. But in both cases, entropy calls the shots. Let's look at your egg first. Inside the raw yolk and albumin are long curly protein chains all folded up in neat little bundles. But as heat hits them, they start to unravel and tangle. They go from organized specific shapes to a dense jumbled mesh, a denatured structure. That's irreversible. You've increased entropy. You've taken something ordered and dumped energy into it until it broke apart in a new, more probable configuration. Now zoom out, way out, in the heart of a collapsing cloud of hydrogen gas, millions of times more massive than Earth. A star is forming. Gravity pulls particles inward. As they compress, they heat up. Eventually, the center becomes hot and dense enough for fusion to begin. hydrogen nuclei slam together and form helium. And that, dear friend, is the cosmic version of cracking an egg. Fusion releases enormous amounts of energy. Why? Because the mass of the resulting helium atom is slightly less than the sum of the original hydrogen atoms. That tiny missing mass? It's been turned into energy, thanks to Einstein's famous equation, E equals mc squared. And where does that energy go? Outward, into space. It warms nearby planets. It fuels life. It powers that burner you made eggs on. It even escapes as cosmic background radiation, Entropy's long-distance calling card. Here's the kicker. When a star fuses hydrogen into helium, it's actually increasing entropy, just like your breakfast did. It's turning concentrated energy, in the form of potential nuclear interactions, into diffused energy, heat and light spreading outward. So the birth of a star and the cooking of an omelette, same law, different drama. And it gets even more dramatic. Stars don't last forever. Once they run out of hydrogen, their internal balance collapses. Gravity takes over. What happens next depends on their mass. Some stars quietly puff out into red giants, shedding their outer layers in a beautiful final sigh before becoming dense, cooling white dwarfs. Others go out with a bang, supernovae that tear themselves apart, scattering heavy elements across the galaxy. Those heavy elements, you're made of them, literally. Your bones contain calcium from stars. Your blood carries iron that was forged in a stellar explosion. The phosphorus in your DNA, star ash. As Carl Sagan said, because we are contractually obligated to quote him at least once, you are made of star stuff. Or, if you prefer, you're an omelette made from cosmic eggs that exploded several billion years ago. And through it all, entropy just keeps increasing. Here's a historical gem for tonight. Sir Arthur Eddington, yes, the Times Arrow guy, was one of the first to suggest in the 1920s that stars shine because of fusion. Before that, people thought stars might burn like coal, which in hindsight is like trying to heat your house with scented candles. It's hard to overstate how elegant and humbling it is that stars and eggs obey the same thermodynamic rules. There's something almost cozy about that, a continuity between the mundane and the massive. You might be wondering, if entropy always increases, does that mean everything is always getting messier? Always decaying? Yes and no. Remember, entropy doesn't mean destruction, it means reconfiguration. It means things are rearranging into states that are more probable, more statistically favoured. In doing so, they release energy. Usable, wonderful energy that drives engines, fires neurons and fries breakfast. Even creativity, building something new, is part of the entropy process. You make a painting. You used paint, air, glucose from your breakfast, and warmth from the sun. That energy goes in, the entropy goes out. Nothing is truly free. Every little miracle has a price. Now here's a deliciously strange fringe theory for you. There's an idea in cosmology that stars themselves might be entropy accelerators, that the universe actually evolves structures, like galaxies, stars, and even life, because they increase the rate at which entropy spreads. It's like saying the universe is designed to unravel itself as quickly and elegantly as possible, and we're part of that unraveling. Cheerful stuff, huh? But seriously, think about it. Stars accelerate the journey toward equilibrium. So do hurricanes, solar flares, and supernovae. And yes, so do you. Every time you digest food, heat your home, or think a thought. So in a strange way, maybe building a star or even just boiling an egg isn't a delay of entropy at all. Maybe it's part of entropy's plan. You settle deeper into your pillow, picturing a distant nebula slowly condensing into a star while, somewhere nearby, someone cracks an egg into a pan. The same laws, the same math, the same silent progression toward disorder, through heat, structure, beauty. There's comfort in that symmetry. You're not isolated from the cosmos. You're an echo of it. So next time you make breakfast, give a quiet nod to the stars. They cooked first. Your eyes close, but your mind keeps wandering. There's something unsettling and oddly comforting about knowing that eggs don't unfry and stars don't unform. Time moves in one direction. Always. Forward. But here's a deeper question that pulls at the sleepy edge of your thoughts. Why do you remember yesterday and not tomorrow? After all, the laws of physics don't care. They're perfectly happy to work backward. If you filmed the dance of atoms and reversed the tape, the math would still check out. No alarms would go off. Nature wouldn't protest. And yet, your memories run one way. This is the mystery of entropy and memory, a tale of time's arrow and your brain's internal filing system. Right now, you're remembering today, the sound of the coffee cup, the softness of your pillow, the strange realization that stars and omelettes follow the same thermodynamic law. But you don't remember next Tuesday. You can't remember what you'll dream in 10 minutes, because your mind, like everything else, is embedded in entropy's current. Memory forms as entropy increases, and once it does, it's fixed. One-directional, just like a crack in glass or a spilled drink. Let's make this more vivid. Imagine a library. In this library, every book represents a moment of your experience, shelved neatly in order. As time passes, new books are added, memories, stored, stable. But the shelves don't allow books from the future. There's no slot for a chapter that hasn't been written. Why? Because memories are physical, not just ideas. They're changes in matter. Neurons in your brain shift shape when you remember. Proteins move, chemicals react. It takes energy to lay down a memory, just like it takes energy to build anything. And once it's built, that memory increases the entropy of your system overall. So remembering is a thermodynamic act, not just a mental one. Here's the twist. If time could truly run backward, you wouldn't just remember the future, you'd unremember the past. Memories would dissolve as your brain rewound itself, like watching ink unspread across a page, or watching a cake reassemble itself from crumbs and heat. And that's not how your brain, or the universe, works. This brings us to Ludwig Boltzmann. He was the same cheerful Austrian who formalized entropy in terms of probability, giving it the statistical backbone it needed to become a cosmic principle. But Boltzmann had a problem. If the laws of physics are time-symmetric, then why does time feel like it has a preferred direction? He suggested that entropy's increase is the reason we perceive time at all. In other words, time isn't something we move through like a hallway. It's a side effect of increasing disorder. The more entropy rises, the more moments are created, the more change accumulates. And you, conscious, blinking, dreaming you, are just riding that wave. So time doesn't move, entropy moves, and we call that motion time. Philosophers and physicists still argue whether this is actually true, or whether our perception of time is more fundamental. But the link between entropy and memory, that's not up for debate. You can't form a memory without increasing disorder somewhere. It's the cost of knowing. Even computers follow this rule. When you write a file, energy is spent. When you delete one, more entropy. As we mentioned with Landauer's principle earlier, even erasing data isn't free. Information has thermodynamic consequences. That photo you saved on your phone? It didn't come cheap, not in entropy terms. Here's a curious fringe idea. Some researchers have speculated that the universe may contain regions, tiny, unimaginable regions, where entropy runs backward. If you were somehow inside one of these entropy-reversing bubbles, you'd still feel time moving forward. You'd remember what we call the future, but your past would be unknowable, forgotten, a sealed vault. Weirder still, you wouldn't even realize it, because your sense of time would flip with the arrow of entropy inside your brain. The movie would play backward, but you'd watch it thinking, ah yes, everything's proceeding as normal. Good luck falling asleep after that. But let's return to something cozier. Think about your childhood home, a corner of a room, a scent, a song that pulls you back. Those memories feel vivid, like you could almost touch them. But they're fragile, just patterns, electrical signals, prone to fading, to changing. Every time you remember something, your brain rewrites it slightly. Memory, it turns out, is not a perfect recorder. It's more like a painter with a faulty brush. Each recollection blurs the lines a little more. Entropy, again, sneaks in. Even our collective memory, history itself, is subject to this rule. Documents degrade, photos fade, oral traditions shift with time. The past drifts little by little toward uncertainty. Unless we put in constant effort, entropy erodes the record. That's why archives need climate control, why museums use glass cases and dim lights, not for drama, though it helps, but to slow down the unravelling. But we never stop it. Now here's a historical nugget. The earliest recorded attempt to link time and memory with physical principles comes from St. Augustine, way back in the 4th century. He puzzled over why we experience time as past, present and future, and why memory seems anchored only to the past. He didn't have the language of entropy, of course, but he felt it. that human longing to understand why the arrow only points one way. And even today that arrow remains stubborn. You can't uneat lunch. You can't unread this sentence. You can't reabsorb the energy it took to make this cozy space around you. The more time passes, the more disorder builds behind you, and the more your mind structures it into something called memory. So you lie here, warm and quiet, nested in a swirl of past experiences, none of which can be reversed. You're the sum of entropy already spent, a collection of moments organised briefly, wonderfully, in a body that slowly, inevitably lets them go. And that's okay, because memory isn't meant to be permanent, it's meant to be experienced, just like life, just like time. And when it fades, it leaves space for the next moment, the next messy miracle, the next breath. You're lying there, lights low, eyelids heavier now, but still awake enough to notice something familiar in this strange journey through entropy. Not the stars, not the eggs, not even the cosmic death spirals. Just your living room. It's not supposed to be a mess. You swear you cleaned it last weekend. Maybe even alphabetized your spice rack. You folded laundry. You vacuumed under the couch. You felt victorious. And yet here we are. Socks have migrated to distant corners. A mysterious spoon lies on the floor like a relic of a forgotten age. The remote has vanished. Crumbs. How are there always more crumbs? Gather like an informal committee under the coffee table. Why do clean rooms still get messy? Entropy, of course. But tonight we're going to slow down and see how this universal principle plays out in your very domestic domain. Because yes, the second law of thermodynamics applies to black holes and the death of stars, but it also explains why your home refuses to stay Instagram-worthy. Let's start small. Picture your room in a perfectly clean state, everything folded, surfaces wiped, books aligned with a slightly smug precision. That state is highly ordered. There's only one, or maybe a tiny handful of ways for all those objects to be in just that configuration. It's statistically rare, unlikely. Now imagine the same room, but messy. Clothes on the chair, that one weird drawer slightly open, 3 mugs, each with a mysterious amount of liquid. There are millions of ways for the room to be messy, but only a few ways for it to be neat. So when you live in that space, walking, snacking, breathing, your actions naturally move the system toward one of its more probable configurations. In other words, mess is easier, more probable, more statistically likely. Not because you're lazy, although no judgment, but because the universe is playing the odds. Every time you pick up an object and use it, you inject energy into the system. That energy gets partially lost as heat, friction, confusion. You move entropy. You don't even have to do anything dramatic. Just existing in a space, shifting air, walking across the carpet, thinking thoughts, nudges the system toward disorder. And let's not forget, tidiness requires effort. Reorganizing a space means applying energy to reduce disorder locally, but that effort increases entropy elsewhere, usually in the form of heat, fatigue, or your growing existential dread while folding fitted sheets. Here's a comforting historical note. Even Albert Einstein's desk was famously cluttered. When someone once showed him a photo of a spotless workspace and asked what it implied, he supposedly replied, "If a cluttered desk is a sign of a cluttered mind, what then is an empty desk a sign of? Zing." But Einstein's clutter wasn't just aesthetic, it was inevitable. Because entropy doesn't care about productivity, it just follows the math. And here's a delightful fringe example. Researchers have built simulations of rooms with tiny robotic agents moving objects randomly. Without programming them to be messy, the system naturally drifts toward clutter. Even in artificial environments, entropy builds unless external energy is constantly applied to maintain order. So unless you've hired a team of tireless entropy-defying robots who live only to sort your mail and realign your coasters, your room will decay, one sock at a time. But what if you did stop fighting it? Let's say you stopped cleaning altogether, not in a gross way, just as a thermodynamic experiment. Over time, your space would become a visual metaphor for the second law. More objects would be out of place. Dust, which is mostly dead skin cells by the way, sleep tight, would settle. Temperature differences would flatten. Smells would mingle. Surfaces would lose their sheen. Eventually, if left long enough, the room would reach what physicists call equilibrium, a state where energy and matter are uniformly distributed, and no more useful work can be done without new input. In short, the room dies. Dramatic, yes, but accurate. Now here's something even stranger. Humans tend to find order in the mess. Your brain is hardwired to spot patterns, even in chaos. So you might convince yourself your space has a lived-in vibe or a functional flow. That pile of books, a reading zone, that cluster of mugs, a hydration station. It's not denial, it's cognitive entropy management. Even in disorder we seek meaning, and sometimes we need a little mess. Perfection is brittle. Chaos is strangely forgiving. But don't worry, order has its place too. Let's say you clean the room again, not because it's required, but because it feels good. That's another entropy trade-off. You're burning calories, creating friction, using time and tools. You're increasing entropy in you and your environment to restore temporary order to a small corner of space. You're not fighting entropy, you're collaborating with it. You tidy not to defy the universe, but to make your own local space briefly coherent. A moment of structure, a pause, and then, inevitably, the socks return. Now here's a weird scholarly debate to snooze on. Some philosophers argue that human culture itself is a system for entropy management. Language, rituals, schedules, rules, ways of organizing the unpredictable. And when those systems collapse, societal entropy spikes. We call it chaos, crisis, or the group text where nobody knows what time dinner is. So your messy room? Just a microcosm of the bigger picture. A fractal of falling apart, but also a canvas for continual rebirth. You can clean it tomorrow, you can start again and again. Each time a small act of resistance, brief but meaningful. That's what life is, remember? Localized order in a sea of increasing entropy. A warm, pulsing system doing its best to stay structured while everything else unravels around it. And when you wake up tomorrow, there might be crumbs again, a sock out of place, a book that slipped off the bed. You'll notice them. Maybe fix them, maybe not. Either way, entropy will smile, because in the end it's not about winning or losing, it's about flow, exchange, the slow drift of order into 100 different forms of gentle, cozy chaos. Just like the room you're dozing in right now. The room is still, the lights are low, and your brain, while heavier now with sleep, still has one more question to chew on before it lets you drift. What if all of this, the socks, the spilled coffee, the feeling of time slipping forward, isn't real? What if you aren't real? What if you're just a fluke, a lone brain floating in a sea of chaos, conjuring up memories of a life you never actually lived? Say hello to the infamous thought experiment known as the Boltzmann brain. It sounds like a band name, or maybe a bad sci-fi movie, but it's actually a deeply unsettling philosophical riddle born from one of the quirks of entropy. You're going to love this. You remember Ludwig Boltzmann, the cheerful guy who helped define entropy as a statistical phenomenon? He was trying to explain how order, like stars, galaxies, and omelettes, could arise in a universe that prefers disorder. His answer: probability. Given enough time, low entropy pockets can spontaneously form. Like bubbles in boiling water, random fluctuations can cause atoms to momentarily assemble into something structured, before falling apart again. This makes sense on large scales. That's how our universe supposedly began, with a low entropy event, a sudden surge of order that eventually unraveled into everything we see today. But here's where things get weird. If you believe the universe is infinite and entropy keeps increasing, then random fluctuations should occasionally create brief, unlikely moments of structure. Not whole galaxies, not entire universes, but maybe just one disembodied brain, floating in space, or nothingness, fully formed for a millisecond, complete with false memories, emotions, and a vivid illusion of the world, including this very moment, right now, in bed, hearing my voice, and then poof, gone, dissolved back into chaos. You shiver a little, not from cold, but from the sheer absurdity of it. Could you be a Boltzmann brain? Just a twitch in the soup? It sounds like a cosmic prank, but the problem is, it's a statistically valid one. Because according to pure probability, it's far more likely for a single brain to spontaneously appear in an infinite universe than for a whole ordered cosmos like ours to unfold from a low entropy beginning. This leads to the Boltzmann brain paradox. If random order is inevitable in infinite time, then shouldn't most observers be disembodied brains, flickering briefly into being? Shouldn't that be you? It's a nightmare version of Occam's razor. The simplest explanation, statistically, is that your entire reality is fake. Sleep well, but don't panic. Most physicists and cosmologists hate this idea. Like really hate it. Why? Because it breaks too many things. For one, it undermines science itself. If you can't trust your memories, your experiments, or the structure of reality, then how can you know anything at all? It's like trying to write a dictionary with invisible ink. Also, it raises ethical and philosophical questions that would make Descartes cry. If consciousness can blink into existence for a split second, alone, unconnected, hallucinating, what does that say about meaning, or suffering, or truth? So, to avoid this unsettling conclusion, cosmologists have gone looking for answers. Some suggest that the universe is finite in time or space, which limits the chance of random fluctuations. Others argue that entropy doesn't work the same way in the quantum realm, or that consciousness can't exist without a sustained thermodynamic process. In other words, no energy flow equals no real thinking. A Boltzmann brain might appear, but it wouldn't be conscious, just a silent ghost. There's also the anthropic principle, which says we can only observe a universe compatible with our existence. Since we see a big, structured universe full of stars and planets, that's evidence we're not Boltzmann brains. But critics counter, isn't that exactly what a Boltzmann brain would think? And so, the debate swirls on. Historians and physicists still argue whether the Boltzmann brain paradox is a serious problem or just a mathematical oddity that collapses under closer scrutiny. But here's a calmer way to think about it. Even if the math allows for a Boltzmann brain to appear once in a while, that doesn't make you one. Because you're not experiencing a single frozen moment. You have continuity, a story. You woke up this morning, you remember brushing your teeth, you have a mild opinion on that TV show with the dragons. That's not a fluke. That's process. Your memories aren't just etched into a brain, they're being constantly refreshed and reinforced by sensory input and biological function. You're burning glucose, producing heat, interacting with a world that responds. That's not a flicker, that's a flow. And flow is the enemy of the Boltzmann brain. Because entropy may allow random moments, but sustained processes, those require structure, time, energy gradients, all the stuff we've been talking about for the last 9 sections, so breathe easy. You're probably not a floating thought bubble hallucinating a podcast about entropy. Probably. Still, the idea sticks in your mind, like a dream half remembered, a reminder that the universe is stranger than it seems, and that our understanding of entropy, time, and reality is still unfolding. Now, here's your quirky bedtime trivia. In 2008, cosmologist Sean Carroll famously argued that if we were Boltzmann brains, the universe should look far more chaotic than it does. Like, dramatically worse. No stars, no order, just random nonsense. The fact that we see consistent laws, stable physics, and decades of reruns on television suggests we live in a truly low-entropy universe, at least for now. So the stars? Real? The room around you? Real? This sleepy narration about brains and chaos? Probably real too, or at least as real as it needs to be. Because in the end, the Boltzmann brain paradox isn't really about doubting your reality. It's about respecting the improbability of existence, the miracle of sustained order, the gift of continuity. You're not just a thought in the void, you're an ongoing act of entropy in motion, a system full of memory, structure, and warmth. Brief? Yes. Fragile? Always. But real. And tomorrow when you wake up and find your socks still on the floor and your coffee slightly cold, you'll know. You were here. You are here. And entropy is watching. You're curled up now, cozy and adrift in your sheets, but still with just enough brain power to wonder, could anything escape entropy? Is there anything in this grand cosmic system that plays by different rules, anything that dances around disorder without paying the usual price? Physicists have tried to imagine just that, and in recent years they've come up with something that sounds straight out of science fiction. Time crystals. Yes, you heard that right. Time crystals. They sound like something you'd find in a video game. Probably glowing, probably guarded by a boss monster, but they're very real, very weird. And they whisper a tempting question. What if some systems don't follow time's arrow quite the way we do? To understand time crystals, you need to first think about normal crystals, the kind you might see in a snowflake, a salt shaker, or a geode in your aunt's living room. Crystals are spatially repeating structures. That means their atomic layout repeats in space, like a neat geometric wallpaper made of atoms. This order is special because it spontaneously forms when the system transitions into a lower energy, more stable state. Crystals don't appear by accident. They require just the right conditions. Now imagine if that same kind of pattern could repeat, not in space, but in time. A system whose state cycles over and over without external input. It doesn't just sit still, it moves, it pulses, it oscillates, forever. That's a time crystal. Discovered in theory by Nobel laureate Frank Wilczek in 2012, time crystals were initially dismissed as physically impossible. After all, any system that moves perpetually without energy input, that sounds a lot like a perpetual motion machine, and those are banned from physics like vampires are from garlic festivals. Why? Because of, you guessed it, entropy. A perpetual motion machine would violate the second law of thermodynamics by continuing indefinitely without losing usable energy. The universe does not allow that. You can delay decay, you can shift disorder around, but you can't build something that never pays the entropy toll. And yet, researchers started to get curious. What if there was a way around that? Not a free lunch, but a cleverly packed one. Enter quantum systems. In 2016, researchers at Google and elsewhere began building systems with many-body localization. A fancy way of saying they used a collection of interacting particles in a carefully designed setup, one where external noise was minimized and energy remained trapped within the system. In that context, under a particular kind of periodic nudging, something amazing happened. The system began to pulse. Not in a chaotic way, not in a decaying, slow winding down kind of way, but in a repeating, predictable rhythm. Like a heartbeat, a system moving in time without losing coherence. That was the first experimental realization of a time crystal. So what does it mean? Have we finally escaped entropy? Not quite. Time crystals don't violate the second law. They still require energy input, just in controlled periodic pulses. They're not self-sustaining miracles. They're carefully isolated low-energy systems operating under extreme conditions that let them display this odd behavior without heating up, without falling apart, and without increasing entropy in the way most systems do. So while time crystals do repeat in time, they're not doing it for free, and they're not infinite. They're just weird. A loophole? Maybe. A rebellion? More like a beautifully choreographed agreement with entropy. A quantum-level deal where repetition doesn't mean disorder, and time flows a little less like a river and a little more like a metronome. Still, it makes you think. If entropy governs the large-scale behavior of the universe, what other strange, small-scale exceptions might be hiding in the quantum basement? What else wiggles or whispers against the rules? Historians, and more accurately physicists, still argue whether time crystals are just a laboratory curiosity or a stepping stone to new kinds of technology. Quantum computers, perhaps. New materials. Systems that exploit temporal order the way traditional crystals exploit spatial order. But even now, the implications are eerie. A system that remembers to move. One that doesn't decay into stillness. A sliver of reality where time becomes symmetrical again. Or at least, less lopsided. Here's a curious bedtime comparison. You, in a way, are a kind of temporary time crystal. You repeat, you cycle, you sleep and wake, inhale and exhale, heart beating in rhythmic defiance of the slow chaos waiting just outside your skin. Your body's not a time crystal in the strict quantum sense. Sorry, but it does maintain rhythm, structure, pattern. And just like a real-time crystal, you can only do it for so long before entropy asks for payment. Aging, after all, is just entropy with good manners. Still, these repeating patterns, your heartbeat, your circadian rhythm, the seasons, the tides, all give the illusion that time might be reversible, or at least predictable. But they're temporary. Eventually noise creeps in, order slips, the pendulum misses its beat. Time crystals? They seem to resist that for now, and that's why they've sparked not just scientific excitement, but philosophical awe, because they hint at a universe more flexible than we thought. One where the arrow of time might bend or shimmer or, even for a moment, pause. That doesn't mean your coffee will unspill or your socks will crawl back to the drawer on their own. But it does mean that time, like everything else we thought we understood, has hidden depths, secrets still buried beneath entropy's tidy statistics. So as you settle in, breathing with the slow, repeating pulse of your own little biological machine, remember, the world doesn't always obey its own rules in obvious ways. There are patterns within the noise, loops within the drift. And even as entropy pulls us forward, melting stars, crumbling rooms, aging bodies, there are systems, however small, that remember to return, to dance, to keep the rhythm, for now. The hum of your thoughts begins to blend with the hum of your surroundings, the fridge, the streetlight buzzing outside, your own breath. Everything feels slower now. You're drifting. But your mind still holds on to a final question, like a thread dangling from the edge of a worn-out sweater. Where does all the lost stuff go? Not just the keys you swear were on the table 5 minutes ago, but the information, the order, the structure. When things fall apart, is anything truly lost? To answer that, you're going to have to walk into the most dramatic room in the universe. It's pitch black, heavy, loud in the way that silence can be deafening. Welcome to the black hole. You've probably heard the basics. Black holes are regions of space-time where gravity is so intense, not even light can escape. They're born from collapsed stars and are, quite literally, the end of the line for mass and energy in many parts of the cosmos. But they're also entropy monsters, in fact the most entropic objects in the universe. That might sound surprising. Black holes feel like the epitome of order, don't they? Smooth, spherical, mysterious, clean. But in 1974, Stephen Hawking turned that idea inside out. He showed that black holes actually have temperature, which means they radiate energy, very, very slowly, via what we now call Hawking radiation. And if they have temperature, they must have entropy. A lot of it. In fact, the entropy of a black hole is proportional to the area of its event horizon, the surface, not the volume. That's bizarre. Most physical objects' entropy scales with how much stuff is inside, but black holes? It's all about the skin. This was the first clue that black holes might not just swallow entropy, they might be it. Concentrated, compact, and horrifyingly efficient. But here's the twist that still keeps physicists up at night. Information seems to disappear into black holes. Imagine this. You toss a book into a black hole, or a laptop, or your entire Spotify playlist. From the outside, all you see is the black hole's mass, charge, and spin. The details, the songs, the words, the passwords are gone, erased, like they never existed. This is a problem. Because according to the rules of quantum mechanics, our best theory for how tiny things behave, information can't be destroyed. It can change form, it can hide, it can scatter, but it can't vanish completely. That would break the fundamental logic of the universe. So we arrive at the black hole information paradox. It's like the cosmic equivalent of throwing your socks into a laundry machine and getting different socks back. Entropy increases, sure, but where did the originals go? For decades, scientists debated this fiercely. Was information truly lost inside black holes? If so, what does that mean for quantum theory? For time? For reality itself? And then came the fringe, mind-bending proposals. One idea was that black holes don't actually destroy information. They just scramble it so thoroughly that it's effectively unrecoverable, like blending a smoothie made of tax records, haikus, and cat videos. Technically, everything's still in there, just mixed beyond recognition. Another theory suggested that information leaks out slowly via Hawking radiation, but this would mean that radiation isn't purely thermal. It carries a faint echo of what fell in. Like whispers riding on light. That's called the black hole complementarity principle. The idea that from one point of view the information stays trapped on the horizon, while from another it escapes. Confusing? Definitely. True? Maybe. Then there's the holographic principle, which came out of these debates like a philosophical mic drop. It says that everything inside a volume of space, like the stuff you threw into the black hole, can actually be described by information encoded on the boundary of that space. So the universe might be a hologram, not in the we're living in a simulation, wake up, Neo kind of way, but in a deeply mathematical sense. That what we perceive as a three-dimensional world is actually encoded on a two-dimensional surface. Yeah, sleep well. But here's the really bizarre connection. Some physicists now think that entropy, gravity, and even space itself might emerge from quantum information theory. That the very fabric of reality is stitched together by how information interacts, flows, and disperses. In that view, black holes aren't just spooky space dumpsters, they're keys to understanding the deepest principles of the universe. And yet they remain profoundly mysterious. For example, what happens when a black hole fully evaporates? When Hawking radiation drains the last drop of mass, and the black hole fades like a tired breath? Does the information escape in the end, or is it gone forever? The jury is still out. Some say it's released in the final moments of evaporation in a sudden burst of pure data. Others argue that the information was always stored on the event horizon and never truly lost. A few even suggest that black holes leave behind remnants, tiny, stable husks that contain all the encoded information in some impossible form. And some, bless their theoretical hearts, think black holes might be portals to other universes, where the information is just moved somewhere else entirely. Historians and cosmologists still argue whether any of this will ever be provable, or whether we're chasing metaphors in the dark. But here's what we do know. Black holes don't break entropy, they embody it. They're the ultimate case study in irreversible processes, the final word in the long sentence of thermodynamics. And maybe, just maybe, your laundry is following the same rules. Ever lost a sock? Of course you have, we all have. You check the washer, you check the dryer, you check behind the machines. Nothing. One sock remains, a singleton. A reminder that entropy, even in small domestic forms, doesn't play fair. But what if your sock isn't lost? What if it's crossed an event horizon, the damp spinning more of the dryer, and become part of a microscopic entropy singularity? You laugh. But also, you kind of believe it. Because if a black hole can absorb an entire star and reduce it to a few characteristics, mass, spin, charge, then your sock too might have simply joined the chorus of missing things that make the universe just a little more disordered. And you're left with the memory. So as you drift off now, your body warm, your breath soft, your thoughts echo one last time across the darkness. Nothing truly vanishes. It only changes, scrambles, fades. But the universe, in all its entropic cleverness, keeps the ledger, even if we can't read it. Your breath is slow now, deeper. The kind that happens naturally when your body finally stops trying to micromanage its own posture. You sink into your pillow, feeling the weight of your limbs, and something subtle clicks in your mind. You're aging, right now, right this second. Not in a panicked way, not in the birthday candle, midlife crisis, oh no, my knees kind of way. More like a slow unfurling, a melting, a leaf in autumn turning not because it failed, but because the system has moved on. Entropy and aging go hand in hand. Biologically, your body is an exquisite machine. It takes in energy, repairs itself, replaces cells, corrects mutations, fights off invaders. It delays the inevitable with more stubbornness than a cat avoiding a bath. But even the best systems can't dodge the second law of thermodynamics. Every process your body undertakes, digestion, thought, movement, even dreaming, comes at a cost. Every bit of usable energy you consume leaves behind a trail of disorder, heat, molecular waste, frayed proteins, 1,000 tiny imperfections that accumulate second by second, year by year. Entropy doesn't attack you, it doesn't hate you, it just keeps tally. Let's zoom in for a moment. At the cellular level, your body is constantly managing entropy. Your cells clean up misfolded proteins, patch damaged DNA, and keep crucial chemical gradients carefully balanced. Mitochondria, those little energy powerhouses in your cells, pump out ATP like overworked baristas, fueling every blink, every heartbeat, every fleeting thought about whether or not you remembered to feed the cat. But over time, the errors add up, the repairs become less precise, the gradients fade. Little by little, entropy starts winning the war of maintenance. This gradual breakdown isn't a flaw, it's not a punishment, it's physics. Aging isn't some dramatic collapse, it's a slow diffusion, an accumulation of probabilities nudging your systems away from precision and into the fuzzier realms of possibility. Like a printed photo slowly losing resolution until all the lines blur together. Still, we fight back. You eat healthy food, most of the time. You sleep, occasionally. You hydrate, begrudgingly. You manage entropy like a particularly anxious accountant trying to delay an audit. And it works, for a while. Your body is designed to resist entropy just long enough to grow, reproduce, and nurture the next generation. After that, nature's contract becomes more flexible. Entropy is patient, and it loves a long game. Here's a historical nugget to snuggle up with. In 1956, physicist Leo Szilard, the same guy who played a key role in developing nuclear chain reactions, proposed that the aging of living beings might be fundamentally linked to information loss. That, as organisms age, they accumulate random errors and lose the clarity of their internal instructions. A slow drift into disorder. He wasn't wrong. Many modern theories of aging revolve around information entropy. The idea that your DNA, your cellular machinery, your epigenetic markers are all slowly being scrambled, like pages of a novel left too long in the rain, now for something even cozier. Ice cream. Specifically, why it melts. You've been here before. You open the freezer, unwrap that perfect pint of Rocky Road and savour that initial scoop. It's glorious. Cold, structured, a balance of fats, sugars, and air whipped into a stable emulsion. Then you leave it out. Within minutes, the structure collapses. The air escapes. The fat molecules drift. The sugars mix unevenly. Your beautiful dessert becomes a sweet, sticky puddle of regret. And once it melts, you can't unmelt it. Sure, you could refreeze it, but it won't be the same. The texture is ruined. Ice crystals form. The emulsion is broken. Entropy has stepped in and said, no take-backs. That's what aging is like. You can slow it down, manage it, even enjoy the ride, but you can't rewind it without adding external energy. A lot of it. More than we currently know how to supply without accidentally turning someone into goo. This is why all those sci-fi tropes about immortality usually end in weird, depressing ways. Freeze a person in stasis. Cool. Wake them up centuries later. Less cool, because while the external world was on pause, entropy never truly stopped. The ice might have slowed the system, but it didn't delete the cost. Everything has a bill eventually. That's why researchers today are studying senescence, the process by which cells stop dividing but don't die. They just linger, useless, dysfunctional, slowly exuding inflammatory chemicals like grumpy old neighbours shouting at kids from the porch. These cells contribute to aging, and researchers are developing therapies to clear them out, senolytics, in hopes of slowing entropy's creep through your tissues. It's early days, but promising. Still, even if we delayed aging indefinitely, we wouldn't have defeated entropy. We'd have just negotiated a longer lease. The house still collapses eventually. Now here's your fringe bedtime theory. Some scientists have proposed that aging is a form of programmed entropy, that organisms are designed, evolutionarily, to let themselves go after a certain point to make room for newer, more viable iterations. A kind of thermodynamic baton pass. It's not a bug, it's a feature, and that's okay, because aging, like entropy, isn't a villain. It's a transition, a changing of states, a shift in structure. You don't become less real as you age, just more complex, more storied, more beautifully disordered. You're not ice cream melting in a bowl. You're a constellation of moments, each one the product of millions of little thermodynamic exchanges. Order built from chaos, memory built from heat. And even as your cells slowly let go of their grip on precision, you continue to exist. You continue to matter, not in spite of entropy, but because of it. Because without entropy, there's no time, no memory, no breath, no sleep, no warmth. So you let yourself melt a little into the mattress now, not in sadness, but in surrender, in gratitude, for all the systems, biological, cosmic, neurological, that have held you together this long. You're a brief, beautiful structure in a universe that specializes in undoing structure. And for now, you're still here. You're still here, warm, listening, eyes barely open now. And maybe somewhere deep in your sleep-soaked mind, a new question ripples through. If entropy means things fall apart, why does the quantum world seem so connected? You've heard about it, even if just in whispers. Entanglement. That spooky, sci-fi sounding quantum phenomenon where two particles separated by miles or even light years can still talk to each other, instantaneously, as if they were holding hands across the void. It doesn't feel like disorder, it feels like order, strange order, alien order. So what happens when quantum entanglement meets entropy? Let's dig in, gently, slowly, and with as little math as possible. In the classical world, the one of coffee spills and socks, you can usually keep things pretty separate. Your spoon doesn't care what your couch is doing. Your cat's opinion of gravity is largely independent of your toaster. But in the quantum world, particles don't always behave as isolated things. They exist in states, weird, probabilistic clouds of maybe, that only become definite when you measure them. Before that, they're in superposition. Schrödinger's cat isn't dead or alive, it's both. Until you check. Now, when two particles become entangled, their states are linked. Measure one, and you instantly know the state of the other, no matter how far apart they are. Einstein called it spooky action at a distance because, well, it spooked him. Entanglement feels like the opposite of entropy. It feels like hyperorder, like particles refusing to let go of each other, even in the face of space, time, or common sense. But here's the twist. Entanglement and entropy aren't enemies. They're deeply entwined. In fact, in modern physics, entanglement is entropy, or at least one flavor of it. Let's say you have a quantum system, two particles A and B, entangled. If you look at the system as a whole, it might be in a very precise, very low entropy state. But if you only look at particle A, ignoring B, A appears random, disordered, high entropy. Why? Because you're missing part of the picture. This is called entanglement entropy, a measure of how much information about the total system you lose when you only look at a piece of it. The more entangled A is with B, the less predictable A is on its own. So entanglement isn't the opposite of entropy, it's how entropy hides. That's deep, right? You only see chaos when you're not looking at the whole truth. Entropy, in this case, is a shadow cast by interconnected order. This is more than just philosophical fluff. It has teeth, real physics teeth. Take black holes again. Yes, them. They always come back. Physicists now think that the immense entropy of a black hole, its tendency to lose information, is actually a result of entanglement between the inside and outside of the event horizon. The information isn't destroyed, it's just entangled in ways you can't access, which is spooky and beautiful, and still not fully understood. There's even a theory, one that sounds suspiciously poetic, that space itself is made of entanglement, that the fabric of space-time emerges from the web of quantum connections between particles. That geometry is a side effect of how deeply things are linked. This is the heart of the AD/CFT correspondence, or what some physicists call the holographic principle. It's complicated, sure, but here's the sleepy version. Maybe the world you see, this three-dimensional space around you, is just a projection of deeper, lower-dimensional quantum interactions. Entangled systems woven together so tightly, they give rise to what we perceive as distance, gravity, and even time. In this view, entanglement is the thread, and entropy is the loom. Together they weave the universe, but let's come back down to Earth. You're lying there, entangled in a way with the environment around you, your skin in constant thermal exchange with the air, your thoughts entangled with memories, smells, feelings, your heartbeat in sync with breath, with temperature, with the muffled sounds beyond the window. You're not separate from entropy, you're woven into it. And entanglement? You're experiencing it all the time, not at the subatomic level maybe, but in how tightly your systems are connected. Touch one thread and others tremble. Pull on one thought and a dozen more arrive. Even your dreams, those strange wandering loops of image and feeling, are entangled with everything that came before, with your day, with your past, with the distant stars whose light now filters through your bedroom window. Here's a quirky fringe fact to fall asleep with. Physicists have demonstrated entanglement with diamonds, literal diamonds. They cooled them, isolated them, and used lasers to entangle the vibrations of carbon atoms across tiny distances. Not atoms, not particles, crystals. The most solid thing you can imagine, entangled. So next time someone says quantum entanglement only happens in weird, rare systems, remind them, a diamond did it. And if a diamond can behave quantumly, maybe the universe is more interconnected than we think. But back to entropy. All this quantum weirdness doesn't overturn the second law. You still can't unfry the egg. You still can't unspill the coffee. Entanglement doesn't reverse disorder. It just explains why disorder appears from our limited view. Because when you lose access to information, when parts of a system become hidden, entropy rises. So yes, the universe is entangled, but we only get to see pieces. And those pieces, they look messy, fuzzy, broken, because entropy is the price of seeing less than the whole. Still, there's peace in that. You don't have to understand everything to be a part of it. You don't need to escape entropy to appreciate the fragile connections holding your world together. Right now, your breath entangles with the air. Your body radiates heat into the room. Your mind floats, connected to ideas that emerge from starlight, coffee cups, and quantum crystals. You're part of the pattern. And entropy? It's just the system reminding you to rest, to soften, to let go of tight control. Because sometimes, the most beautiful order comes from letting things fall apart and trusting that the pieces are still connected in ways you can't quite see. Your body is still now, heavy in the best way. You've floated through black holes, rearranged time with quantum threads, even made peace with the entropy of a melting dessert. But here comes another thread tugging gently at your thoughts. If entropy always increases, how did we get so complex? You, for example. You're not just a collection of particles bumping into each other randomly. You're cells within organs within systems. Your memories and preferences and playlists. Your structure, purpose, pattern. And that's not even getting into spiders or snowflakes or ecosystems. It almost feels like a contradiction. If the universe wants to fall apart, why does life, evolution, progress, complexity happen at all? Tonight, let's wander gently into that strange tension between entropy and evolution. Let's start simple. Picture a rocky planet. No trees, no Netflix, just hot rocks and cooling lava. Now add time, lots of it. Stir in some carbon compounds, a little liquid water, maybe some lightning or undersea volcanic vents. Then suddenly something shifts. Molecules start copying themselves, clumsily at first, but enough to survive, mutate, repeat. Life is born. And here's the kicker. This doesn't defy entropy, it's driven by it. Life doesn't fight disorder, it harnesses it. Your cells, your metabolism, your brain, they're all engines that turn low entropy inputs, food, oxygen, sunlight, into usable work, producing higher entropy waste along the way. Carbon dioxide, heat, noise, dead skin cells. Life is a machine that increases entropy faster than if it didn't exist. You heard that right. Evolution speeds up entropy, and evolution. It thrives in systems where energy is flowing, where there's a temperature difference, a pressure imbalance, a chemical gradient, all of which are products of a universe trying to even itself out. No imbalance equals no change. No change equals no mutation. No mutation equals no evolution. And without evolution, no jellyfish, no pine trees, no dogs in sweaters, no you. So evolution doesn't contradict the second law. It's riding it like a cosmic surfboard. Here's a fascinating mainstream fact to chew on as you drift. In 2014, researchers published work showing that self-replicating molecules, the kind that kick-started life on Earth, arise naturally in systems that are driven by an external energy source and that dissipate entropy effectively. Translation: when the conditions are right, life is almost inevitable, not because the universe loves life, but because life is really good at helping entropy do its job. Here's the poetic version. Life is entropy's assistant. It organizes temporarily only to tear down more efficiently. But that's not cynical, that's magnificent. Imagine evolution as a sculptor with very weird tools. Every time a random mutation improves energy efficiency, even a little, it gets passed along. The organism survives, reproduces, passes on the trick. Over time, this leads to eyes, wings, fins, feathers, brains, memories, language, Spotify algorithms, and all of it fueled by an endless stream of energy from the sun, converted and degraded again and again. But every step of the way, entropy increases. Even the process of natural selection at its heart is a sorting mechanism that increases entropy in the larger environment. The organisms that survive do so by using more energy, producing more waste, building complexity while feeding disorder into the surrounding world. And the ones that don't survive? Their energy is recycled too. Nothing is wasted. Nothing escapes. Now for your quirky fringe moment of the night, a few researchers in thermodynamics and biology have proposed the maximum entropy production principle. This idea suggests that systems, including ecosystems and economies, evolve in ways that maximize the rate of entropy production. In other words, the universe doesn't just tolerate life, it might actually prefer it, because life spreads disorder faster and more efficiently than rocks or lava ever could. Think about that for a second. You, lying in bed right now, are the result of billions of years of entropy optimization. Not just survival, not just reproduction, but the emergence of beings who can process information, tell stories, and burn through calories in a surprisingly stylish hoodie. Even culture, technology, and society are forms of entropy acceleration. Cities are complex, yes, but they also burn enormous amounts of energy to maintain their order. They are heat engines in disguise. We build, yes, but in building, we scatter. We produce light, heat, carbon, noise, data. And in doing so, we uphold the second law, faithfully, beautifully. Still, Evolution comes with baggage. With complexity comes fragility. Ecosystems can collapse. Civilizations too. Brains forget. Muscles tire. What took billions of years to refine can vanish in moments if the energy flow is disrupted. Remember that phrase we keep returning to, local order, global disorder. Evolution is local order. It's complexity with a deadline. But it's also a celebration of what entropy makes possible. Without the second law, the universe would be static. No movement, no gradients, no reactions, a perfect equilibrium. And perfect equilibrium is just a fancy way of saying nothing ever happens. So when you hear entropy, don't think of decay. Think of opportunity, the chance for change, the space for novelty, the pressure that forges life, complexity, consciousness. You are, in some ways, a temporary ripple, a little bump in the smooth surface of what would be. But that ripple holds memories, dreams, bad puns, curiosity. Evolution didn't beat entropy, it danced with it. It still does. And even now, as your breath slows and your thoughts spiral toward dreams, your body is participating in the grand negotiation, holding on to structure a little longer so that your warmth can drift gently into the night air. You're a process, not a product. Your entropy in motion, shaped however briefly into the form of a human, and what a lovely shape it is. Your breath rises and falls in a rhythm older than language. You're floating now on the gentle edge of sleep, warm and just curious enough to ask one more thing. Did anyone see this coming? All this talk of entropy, time's arrow, the collapse of order? Did anyone, long before thermodynamics and black holes, have a hunch about it? Let's time travel, slowly, back through the layers of history to a world without equations or lab coats. A world of togas, scrolls and philosophers pacing under fig trees. Because yes, the ancient Greeks almost got it. They didn't have the word entropy, of course, but they had questions, big ones. Questions like, why do things change? Why does fire rise and water fall? Why does the past feel different from the future? And from those questions came some surprisingly close guesses. Start with Heraclitus, the moody philosopher from Ephesus, writing around 500 BCE. He famously said, everything flows, and you cannot step into the same river twice. His whole worldview was about change, how it's not just something that happens, but something that is. No permanence, just motion, just process. Sound familiar? Heraclitus didn't have the math, but he had the vibe. He saw the universe not as a static thing, but as a dynamic unravelling, an eternal becoming. You can practically hear the entropy humming under his metaphors. Then there was Anaximander who took things a step further. He believed the world was born from an infinite, undefined apeiron, a formless source. From that came opposites, hot and cold, wet and dry, light and dark. The universe, he said, was driven by a kind of cosmic injustice, where these opposites struggled for dominance, constantly rebalancing. Change wasn't just natural, it was necessary. And in rebalancing, the universe moved. Entropy in a toga, basically. But the real proto-thermodynamic thinkers were the atomists. Leucippus and Democritus, in the 5th century BCE, imagined that everything was made of tiny, indivisible particles, atoms. These atoms moved through the void, clashing, bouncing, combining. According to Democritus, the universe had no direction, no purpose, just atoms rearranging endlessly. Things came together, fell apart, reformed. Life, death, stars, rivers, it was all just atomic shuffling. Now that's entropy. Sure, they were off on some details, like thinking atoms were literally uncuttable. Spoiler, they're not. But the idea that order and complexity are just temporary arrangements of matter? That's practically a thermodynamic thesis. And then there was Lucretius, a Roman poet in the 1st century BCE, who tried to explain all this in verse. His epic poem, De Rerum Natura, on the nature of things, described a universe of eternal motion and decay, where everything breaks down into invisible parts. He even described entropy-like phenomena, the slow collapse of buildings, the aging of bodies, the fading of smells and sounds. He didn't call it entropy, but he understood that nothing stays pristine forever. His words echo through time. Nothing in the body is made to last forever. True then, true now. But here's the philosophical twist. Not everyone agreed. Plato and Aristotle, for example, weren't so keen on the idea of a chaotic, entropic world. Plato believed in eternal perfect forms, unchanging blueprints that existed beyond the physical realm. In his view, the world was messy because it was a flawed copy of a perfect original. And Aristotle saw motion and change as striving toward purpose, everything moving toward its final cause, like an acorn growing into a tree or a spark becoming a flame. To them, disorder wasn't a law, it was a blemish, a failure. They wanted cosmic order, not cosmic decay. So you can see why thermodynamics might not have fit neatly into their worldview. Still, they laid the groundwork. Aristotle's studies of motion and causality eventually fed into centuries of science. And even Plato's obsession with ideal forms nudged people toward thinking in systems, even if he wanted those systems to last forever. Spoiler again, they don't. Now here's a historical side note to soothe you. For most of human history, people didn't think time had a direction. Ancient calendars were cyclical, based on the seasons, the moon, the harvest. Stories were told in loops. Life was a pattern that repeated: birth, death, rebirth. Entropy hadn't yet drawn its arrow across the sky. It wasn't until the scientific revolution, and later the industrial revolution, that we started to see time as linear. Suddenly we had clocks, gears, trains, engines, systems that degraded, rusted, wore down. Entropy introduced irreversibility into our thinking, and with it came the idea that maybe the universe wasn't looping, maybe it was drifting, from order to disorder, from simplicity to complexity and back again until it all ran out. But the Greeks, they were already sniffing it out. They didn't have steam engines or telescopes, but they had observation, philosophy, imagination. They knew things fall apart, but they just didn't yet know why. Today, we give that why a name: entropy. We draw the graphs, run the simulations, write the textbooks. But the questions are the same ones Heraclitus asked by firelight, the same ones Lucretius whispered in verse. Why do things change? Why does time move forward? Why does nothing ever stay? And the answer, now, is gentle, patient. It doesn't scold or mourn, it simply is. Because the universe loves possibility more than perfection. Because change isn't the enemy, it's the game. So as you drift off, entangled with blankets, warmed by heat you didn't know you were radiating, remember, you're not just a witness to entropy, you're part of a tradition. A long, curious, slightly confused line of humans staring at the stars and wondering, why do things fall apart? And more importantly, why are they so beautiful on the way down? The cathedral stands at the edge of a crumbling town, bones of stone wrapped in ivy. Its stained glass windows, once vibrant with divine light, are cracked. Not broken, just weathered. There's a softness to the decay, a peace. The air inside smells like old wood and dust, warmed gently by sunlight that now seeps through holes instead of prisms. You run your hand along a stone column, cold, solid, etched by time, not by hammers or chisels, but by rain, by wind, by the quiet friction of centuries. This place isn't just aging, it's yielding. And entropy is everywhere. Now you're ready to see it in a new light, not just in physics or biology or cosmic thought experiments, but in art and architecture, the places we build, the beauty we try to capture, the expressions we shape, carve, paint, and erect to push back against the inevitable. But entropy waits, patient, respectful even. It doesn't vandalize, it reclaims. So let's talk about why art breaks, why buildings fall, and why we keep creating anyway. Imagine a painting. Let's go with something dramatic. An oil canvas from the Baroque period, full of angels, drama, and unnecessary clouds. For a few centuries it hangs in a cathedral like the one above, lit by candlelight and awe. But slowly the paint starts to crack. The varnish yellows, pigments fade, entropy at work. Not destroying but redistributing molecular order. The organized layers of pigment and binder slowly breaking down, the energy stored in those bonds slowly radiating away into the cool air. Now you might think, sure, that's just time doing its thing. But remember, time is entropy in motion. Art ages because it is made of things, molecules, atoms, matter that wants, statistically speaking, to relax into more probable states. So even the Mona Lisa smiles under the weight of entropy. Same goes for buildings. Let's say you build a house. You measure, cut, fit, align. You fight against randomness with every screw and level. But the second you stop applying energy, maintenance, cleaning, repairs, entropy starts eroding it. Paint peels, wood swells, tiles crack. It's not bad luck, it's physics. The universe is saying, you organised this? Cute. Let me offer some edits. Even our most ambitious structures, cathedrals, pyramids, skyscrapers, eventually bend to the second law, some faster than others. In humid air, iron rusts. In dry heat, sandstone crumbles. In freezing climates, water expands inside concrete cracks until they split open like forgotten walnuts. Here's your mainstream historical moment. The Colosseum in Rome, completed in 80 CE, once held over 50,000 cheering fans. Today, it's a skeleton of arches and stone, picked apart by time, weather, and repurposed materials. And yet, it's still beautiful, maybe because it's been softened by entropy. There's something haunting about ruins, something calming. Why? Because they show us the arc of all things. They whisper, this was made, it was grand, it mattered, and now it's dissolving. But let's zoom in. Entropy doesn't just touch the structure, it touches the idea. Take music. A perfectly rehearsed piece, say, a string quartet performing Mozart, is a momentary arrangement of vibration and coordination. But the second it ends, the room falls silent. The sound disperses, the notes fade. You can't scoop them back into the instruments. You can replay the song, yes, but the performance is gone. The entropy of the room has increased. Some of the musicians sweat a little. The strings stretch. A breath is lost. Art is performed order, but always fleeting. Now let's drift into something more fringe. There's a philosophical idea, still debated today, that decay enhances meaning. It's tied to the Japanese concept of wabi-sabi, the appreciation of impermanence and imperfection. A cracked bowl is not ruined, it's interesting. A weathered sculpture doesn't lose its power, it gains gravitas. In this view, entropy is what gives beauty its weight, because nothing perfect can stay. Because to see something begin to crumble is to know that it once stood and still echoes with that former purpose. Think about urban ruins, abandoned theme parks, derelict train stations, factories overtaken by moss and silence. There's a whole genre of photography dedicated to capturing these spaces. Ruin score, they call it. It's both sad and serene, because in every rusted bolt, in every shattered pane, entropy is finishing someone else's sentence. And yet, we keep building. Artists paint, architects sketch, sculptors chip away at stone that will someday fracture, not because they're defying entropy, but because they're collaborating with it. Art is a contract with time. I'll create and you'll undo, but slowly. Let the echoes linger. And here's the cozy truth. Even entropy can't erase everything. Meaning isn't bound to molecules. A song may fade, but its memory persists. A temple may fall, but the story survives. A child's drawing may wrinkle and crumble, but the gesture, the act of creation, ripples outward. Here's your quirky bedtime fact. In 1972, artist Dieter Roth created a sculpture made entirely out of cheese. Yes, cheese. It was meant to decay in public, melt, mould, collapse. A literal act of watching entropy unfold. People were horrified, also delighted, because it reminded them even the ridiculous can reveal truth. And that truth is this: art doesn't need to last forever. It needs to exist now, just like you, just like this moment, just like the cathedral that still stands, whispering stories in cracked glass and softened stone. So as you close your eyes, drifting off beneath whatever artwork you keep near your bed, maybe a framed print, maybe a child's drawing taped to the wall, know this: it too is unravelling. But that doesn't make it less beautiful. It makes it real. You're wrapped in quiet now. Even your thoughts are starting to tread more softly, like visitors in a museum after closing time. But one last paradox flickers across your mind like a half-remembered equation. If entropy always increases, and if the fundamental laws of physics are reversible, why can't I untoast toast? Why can't the arrow of time just flip? Let's sit with this strange tension between reversible equations and irreversible reality. Because here's the mind-bending truth. Most of the core laws of physics, the equations that govern how particles move, how forces interact, how light travels, don't care about time's direction. They work just as well backward as forward. You could reverse time in the equation, swap t for negative t, and the math still checks out. Newton's laws? Symmetrical. Maxwell's equations of electromagnetism? Also symmetrical. Even quantum mechanics, as weird and glitchy as it is, mostly plays fair with time until you start making measurements. More on that in a bit. But here's the catch. You live in a world that clearly does not go backwards. You don't see broken eggs reassembling. You don't see coffee unmixing from cream. You don't, no matter how many times you try, see toast untoasting itself into warm bread. So what's going on? If the micro-level laws are reversible, why is your experience of the world so one-directional? The answer, once again, is entropy. Entropy doesn't appear in most of those core equations. It's a statistical concept, a way of describing how large groups of particles behave when you don't track every detail, and that's the key. At the particle level, sure, everything's reversible. If you knew the position and velocity of every single molecule in a broken egg, you could, in theory, run the clock backward and watch it leap back into the shell. But the odds of that happening on their own? Astronomically low. That's what entropy gives us. Direction. Not because the rules demand it, but because the probabilities do. In other words, it's not that time is fundamentally one way. It's that the universe almost always moves toward more probable states, and those states happen to be more disordered. It's like shuffling a deck of cards. There's only one way for it to be perfectly ordered, ace to king, all four suits, but there are billions of ways for it to be random. So every shuffle, every energetic interaction nudges it toward chaos. And so it is with life and toast and socks and galaxies. Now here's where things get quantum. In quantum mechanics, when you're not measuring anything, particles exist in superpositions, all possible states at once. But once you observe them, they collapse into a single outcome. This measurement process, it introduces irreversibility, not because the universe demands it, but because we do. Our act of measuring breaks the symmetry. It turns possibilities into a single reality. And with that collapse, we lose information. Entropy increases. So some physicists argue that consciousness itself might be part of the reason time flows one way. Because we observe, because we remember, because we make marks, footprints, stories, measurements, and those can't be unmade. Others go deeper, suggesting that the thermodynamic arrow of time is just one of several arrows. There's the psychological arrow, we remember the past, not the future. Thermodynamic arrow, entropy increases over time. Cosmological arrow, the universe is expanding, not contracting. Radiative arrow, waves like light or sound move outward, not inward. Quantum arrow, measurement collapses wave functions in one direction. And the strangest thing is, they all seem to point the same way. Historians of science still argue whether this alignment is coincidence, consequence, or a deep law we haven't cracked yet. But the fact remains. No matter which arrow you look at, time moves forward. Even if the math says it doesn't have to. Now here's a comforting image to tuck into your blanket with. Imagine time as a spiral staircase. From above, the steps look like a circle, like you could go forward or back. But if you tilt your head, you'll see that each step moves upward or downward, depending on your frame. The direction depends on perspective, but movement happens, and it carries you away from where you were. Entropy is that movement. It ensures that each moment is new, that no step can be truly retraced. Even if you turn around, the height has changed. The state has shifted. No matter what, you are not where you were. Here's a quirky historical tidbit. In the early 1900s, physicist Joseph Loschmidt pointed out this very paradox to Boltzmann. If all particles are governed by time-reversible laws, then entropy shouldn't increase. It's called Loschmidt's paradox, and Boltzmann's response was simple but profound. We don't track every atom, so what we see isn't the absolute behavior of matter, but the statistical unfolding of possibilities. Translation: we see what's likely, not what's possible. So why can't toast untoast? Because it's possible, but not probable. In the same way that air could, in theory, all rush to one side of the room, but never does. Because the more particles there are, the more ways disorder can grow, and the fewer paths exist to undo it. So you keep walking the staircase. You don't fall back through childhood or memories or spilled coffee. You move ahead, one breath at a time, through a world where time seems to flow only forward. because that's how entropy rolls the dice. And your place in that story, it's not trivial. You're the result of irreversible processes. You are the consequence of entropy, of stars burning, molecules colliding, toast becoming toast. But you're also something else. You're a witness, a mind shaped by memory and anticipation. A being who feels time not as numbers ticking past, but as change, as loss and creation braided together. You live inside the math, but you also give it meaning. And maybe, just maybe, that's why time only flows one way for you. Because the only story worth living is one you haven't finished yet. Your pulse is slow now, like a metronome at rest. The sheets are warm, the air is still, but your mind, soft and wandering, lands on something almost emotional. Is entropy trying to tell us something? Because even without equations or graphs or cosmic background radiation, you feel it, don't you? That slow drift of things away from what they were. The socks that don't stay folded. The phone battery that never lasts as long as it used to. The way your once flawless spreadsheet somehow becomes an accidental patchwork of chaos after one shared edit. Entropy isn't just in the stars, it's in your laundry, your emails, your life. Which brings us to tonight's quiet truth. Entropy's moral. Nothing stays perfect. And that's not just a law of physics, it's a lived reality. Think about perfection. The fresh snow before footprints, the just cleaned room, the flawless page before words are written. We chase these moments, we celebrate them, but they're fragile. They collapse the moment anything interacts with them. Your boots, your thoughts, your hands. That's not failure, that's thermodynamics. The universe resists permanence. It prefers possibility over precision. And the moment you impose order, entropy gets to work, gently, patiently, peeling it apart. Even in your mind, a perfect memory fades, a belief becomes complicated, a relationship shifts, a plan changes. Entropy isn't just in physical systems, it plays out in emotions, intentions, identities. And here's the twist. That's what makes things interesting. Because perfection, it's static, untouchable, a still photo with no story. But imperfection moves, it evolves, it invites interaction. A spotless kitchen might be satisfying, but it's the dinner mess that tells the story. A freshly made bed is nice, but the imprint of your body in the blankets after a nap, that's entropy, and it feels like home. Perfection demands isolation. Entropy invites life. Let's pull this into history for a moment. In the 1700s, the Enlightenment gave us the ideal of rational order. Everything could be improved, systematized, perfected, through logic, structure, reason. But then came the Romantics. Poets, painters, thinkers who loved the idea of things falling apart, crumbling castles, overgrown gardens, half-finished symphonies. They didn't see entropy as loss, they saw it as texture. Even today, designers and artists embrace the patina of aging, the crackle of vinyl, the faded denim, the coffee-stained notebook. These are not signs of failure, they're badges of use, signs of presence, and yet, our culture still obsesses over perfection. We polish, filter, optimize, curate. We delay wrinkles, we chase symmetry, we stack pillows like they're in competition, but entropy always wins. Not because you're doing something wrong, but because the world is built to change. Perfection is the exception. Entropy is the rule, even in the universe at large. Galaxies swirl into spirals of stars and dust, full of gravitational drama, and yet they too slowly degrade. Stars burn through their fuel. Solar systems destabilize. Cosmic structures stretch and thin until the filaments of matter themselves begin to quiet. Everything you admire out there, it's on the clock. Here's a mainstream cosmological note. The cosmic microwave background, that gentle afterglow of the Big Bang, is slowly cooling. Right now, it's just a few degrees above absolute zero, and eventually, it will fade entirely. The last whisper of a once fiery universe dissolving into equilibrium. Entropy doesn't rush, it waits. And in the meantime, it teaches that everything you love will shift, not vanish, not disappear, just soften, widen, reshape. Even your idea of who you are. Because identity too is a structure, a complex web of memory, habit, intention, and entropy reaches into that web, tugging gently, changing your routines, your preferences, your fears, You're not the same you were 5 years ago. That's not a crisis. That's thermodynamics. So maybe it's time to stop resisting, not to let everything go, but to expect the unravelling, to plan for change, not in fear, but with curiosity. You fold your socks not to beat entropy, but to make the next morning easier, knowing full well they'll be unfolded again. You clean the kitchen not to preserve perfection, but to reset the stage, to begin again. And beginning again is the gift entropy gives you. Because if nothing stayed perfect, then nothing is too broken to begin again. Every system is in motion. Every mess is just a step on the staircase. Every mistake, a little chaos added to the mix, a push forward, not backward. You're not failing when things fall apart. You're participating in the most consistent process in the universe. Here's your quirky fringe bedtime fact. In certain Buddhist philosophies, impermanence is not just accepted, it's celebrated. The practice of creating sand mandalas, intricate patterns made grain by grain, is followed by their ritual destruction. Hours of delicate work swept away in minutes, because beauty doesn't need to last to be real. And structure doesn't need to stay to have mattered. So let the socks get unfolded, let the room get messy, let the toast become toast and the coffee go cold, and the thoughts fade at the edges. Nothing stays perfect, but that was never the point. You are here, you made something, you changed something, and even as entropy whispers that all structures will eventually yield, it also reminds you that all stories come from movement. And you're still moving. You're almost gone now, drifting gently, only half tethered to the world of thoughts. But before sleep fully claims you, there's just one more question floating at the edges. If everything falls apart, why doesn't that feel depressing? Why doesn't entropy, this slow, unstoppable slide into disorder, fill you with dread? Because it could, right? If the universe is unravelling, if all structure fades, if time's arrow points only one way and all paths lead to stillness, then where's the hope? Where's the joy? And yet, here you are, tucked in, breathing, not panicked, just curious, maybe even, strangely, comforted. Because tonight we finally say it aloud. Entropy is not the villain. It's the reason anything happens at all. Without entropy, there is no time, no sunrise, no memory, no story. You live in a universe that doesn't just allow change, it requires it. That's what makes it interesting. That's what makes you possible. The second law of thermodynamics says the total entropy of a closed system always increases. Yes, but look closely at what that permits. It allows temporary islands of order to appear. Brief eddies in the cosmic stream. Galaxies, snowflakes, you, not in defiance of entropy, but as a function of it. Without disorder to spread, there would be no gradients, no energy flow, no way to power complexity. Without entropy, a cup of coffee wouldn't cool, but neither would your neurons fire. No motion, no music, no meaning. Entropy is not chaos, it's potential, flowing downhill, and life. Life is what happens while riding that current. You aren't falling apart, you're unfolding, you're a process. Warm, breathing, full of structure that rearranges itself 1,000,000 times a day just to keep going. And even if your form is temporary, your story isn't meaningless. Because what entropy takes in structure, it gives in space. The space for new things, new patterns, new moments. It's like a forest fire. Destructive, yes. But after the burn, nutrients are released. Seeds sprout, life returns. Not the same as before, but that's the point. Even decay makes room. Here's your mainstream science hug for the night. Stars die so that planets can live. Supernovae scatter the elements that make up your body. Every atom of calcium in your bones, iron in your blood, phosphorus in your DNA. It all came from a star that collapsed and exploded. Destruction created the ingredients for life. That's entropy. Not an ending, but a transformation. And here's your fringe bedtime curiosity. There's a theory, called ontological openness, that suggests the future is not just unknown, but unknowable. That the unfolding of entropy isn't just a process, but a creative act. The universe isn't marching toward a set outcome, it's improvising. You are part of that improvisation, a moment that couldn't be predicted even by the laws that guide everything else. You're not here despite entropy, you're here because of it. Even your dreams tonight, those shapeless, playful, shifting collages of memory and thought, are thermodynamic dances. Your brain, cooling slightly in sleep, rerouting its signals, letting structure loosen and reassemble. letting go to make room. So no, this isn't depressing. It's honest, gentle, beautiful. Entropy doesn't erase meaning. It makes meaning possible. Because when you know that everything is temporary, that nothing lasts forever, that every perfect moment will fade, you start to pay attention. You cherish. You show up. You marvel at a warm mug, at folded socks, at a half-melted sundae, at a friend's laugh fading into silence. You appreciate the shape things take precisely because you know they won't hold it forever. So here you are at the end of this journey, not broken but unfolded, changed, a little wiser, a little sleepier, and somewhere, Entropy smiles. Not because it won, but because it always meant to share. The light of stars, the crackle of fire, the whisper of thought, the softness of dreams, it's all yours, for a little while. So now, just breathe. There's nothing left to do, nothing left to fix, nothing left to hold. Let the thoughts dissolve like mist. Let your muscles forget the shape they've been holding all day. Let your heart beat slow, as if it too is remembering that it's allowed to rest. Entropy is not rushing you. There's no deadline, just the soft drift of molecules, the gentle balancing of heat, the fading of tension into stillness. Even now, the temperature difference between your body and the air is equalizing. The universe, always tidy in its own disorderly way, is smoothing the edges between you and everything else. And you? You're safe here. Nothing has to be permanent to be precious. You're allowed to let go of the need to keep it all perfect. Because the beauty isn't in what stays, it's in the shimmer that fades, the breath that exhales, the sock that refuses to match. You've walked through time, through stars, through black holes and brains and broken eggs, and here at the end of the story, the truth is softer than you expected. Yes, things fall apart, but only so that something new can unfold. So, sleep now. Entropy will take the night shift, and you, little temporary miracle, can simply rest.